Hi, I'm Sandra.
I'm Steven.
And this is BroadBrush.
An art classifier.
So what it does is, given a piece of art, BroadBrush will determine the artist and era from which it came.
So our reasons for doing so is that we'd want to bring art classification into computer vision, in addition to the fact that this could potentially inform making a model for something like detecting fraudulent art.
So as an overview, what we want to do is we want to place our nets in series. What that means is we have two models, one predicting the era, one predicting the artist. We'll take the output from the era prediction and feed it into what our artist model predicts, and that's 24 artists. So we'll only take the 4 artists from that era, and then just take the max of that one in hopes to improve accuracy.
So overall, we had 6 eras that we wanted to classify, in addition to 24 artists that we wanted to classify, for almost 9,000 images, all from the WikiArt dataset.
For pre-processing, we began by going through each of the datasets, or the entire dataset manually, and taking out any sketches, studies, or any artwork that wasn't representative of the artist or era. Then we began cropping, doing a random 300 by 300 pixel cropping of each image. And then to augment the dataset, we took multiples of these from the same images. But to clarify, between training, test, and validation, the same image didn't appear across those. So all the croppings from one image were in training, another validation, another test.
In addition to this, we also added a Gaussian blur, normalization, and a random horizontal flip. The random horizontal flip was more of an empirical observation that increased our accuracy, but the Gaussian blur was because we eventually chose to use a ResNet, and we figured that the ResNet inputs on the pre-trained layers would probably have involved a Gaussian blur somewhere along the line. So we figured it would help our accuracy if we involved a Gaussian blur with ours.
So for our models, we ended up with 5, beginning with our baseline. So our baseline, we decided to compare color vectors. We thought we would do RGB, but turns out that's not possible. So we switched into a CIE lab color space, which finds the difference between these vectors with the delta E function, very high level. But so comparing this color vector of one piece of art to the average color vectors of one for an era or one for an artist yielded about a 30% training accuracy, or just a 30% accuracy. There was no training, validation, or testing. Moving on, we went into our CNNs, where the name of the game was one layer and then many kernels, because we thought the distinguishing characteristic would be brush strokes. We were able to overfit, which was good, but as it turns out, we couldn't achieve any accuracies above 50%, so we decided to move on.
Right, so we decided to use transfer learning with the ResNet. The ResNet that we selected had 101 layers, and we had a low learning rate on the pre-trained layers, which we used to adapt it to our particular problem. In addition to that, you can notice that we got an 86% validation accuracy for our error ResNet. But the accuracies that you see for the artist ResNet are actually the accuracies produced without the linking together of the two networks that we discussed previously.
So just to show the overfitting of our CNNs and our ResNets to see why we'd made the switch. As you can tell, we're overfitting pretty harshly on CNNs, but with ResNets, we're able to train and validate properly.
So here are the results for era. As you can see, we have a very strong diagonal in our confusion matrix, which is good news. And you can also notice that the point of confusion is at the top right of the graph. And that has 21 points of confusion between the Baroque period and the Renaissance, which is actually 2 very similar periods. If we look at the next image, you can see this is an example of a Renaissance and Baroque painting. They both involve very similar colors, very similar textures, and very similar themes as well.
Moving on, this is our confusion matrix for our artist, and this is our artist model once it's been fed the prediction from the era. So as we predicted, our test accuracy, it went up from 60% to 80.4%, which is a really nice increase. The points of confusion are at the top where you see a value of 10, and towards the bottom where you see a value of 10. Those are actually between artists of the same era, which is again an area where people might mess up, which we predicted. So at the top, it's Renaissance artists. At the bottom, it was Baroque artists.
So the key takeaway here was that the actual making of the models themselves was something that was fairly quick and pretty easy to do. However, the real bottleneck was the data set itself. It was very difficult to find eras that had sufficient amount of data that you could actually classify. Like one thing that we stopped classifying was fauvism, because we could only have like 200 pictures for the whole era, which wasn't sufficient for our data set.
The computing power was something we didn't anticipate. We thought we could do a lot on our own, but we had to quickly switch into And not our CPUs, basically. Our computers got very hot.
In addition to that, we were really amazed at how rapidly the model learned once we finally got to the ResNet. It did something that would probably take us months to study to actually get to that level of accuracy on our own, and it did it in a few minutes. That probably says something more about us than it actually says about the ResNet itself, but still it was very impressive.
Given more time, we would try to improve our CNN results. The reason we made the switch over to TransferNet so quickly was just because of the time constraint. But given more time, we'd try and tune some more layers, hyperparameters, et cetera, to see if we can get accuracies above 50%.
Mm-hmm. And to clarify with that, it just would have, we don't expect that our model would have performed better than the ResNet. However, it would have deepened our understanding of the problem had we designed the model ourselves a bit more detailed.
Thanks for listening.
Thank you very much.
That's actually quite interesting, the journey you went on to get through those things, and it's neat to see it's interesting to see the sequence network that's sort of a mini algorithm to pick the error first. That's cool. What CPUs did you end up using? I thought you were going to try Google Cloud.
So we used Google Colab first, and the problem with Google Colab was that especially with the ResNet would actually load too much memory onto the GPU itself. So we actually had to specialize our code, and then we had the help of Matthew Zhang, fortunately, who let us use the Vector Institute GPUs to run our stuff.
So you didn't try
We did try Google Cloud Computing, but in the end it was like, I couldn't get the download done, and then like you have to get like verified and stuff too. And then Matthew was there, and he was like, look, I can help you with this if you want, which was very fortunate that he was there.
So baseline was our computers, CNNs were Colab, and then TransferNets were Vector Institute.
Yes.
But you're also showing the power of transfer learning.
Mm-hmm.
I learned a lot. That's very cool. I didn't quite understand one explanation you gave for why there's a blur. You said it's because of ResNet.
Right. So when I was reading some of the documentation on the ResNet 101 for MATLAB, so that's what I found. I actually didn't find any of that for HyperX itself, but they said that the input images and the images that was trained on was actually with a Gaussian blur for those images. And they're not using ARC, right? So they're like classifying things like keyboards and computer mouse and stuff like that. So the blur would have, it was another empirical decision too. Like
Yeah,
also
and blurring, by the way, is an attempt at generalization, right? So
Yeah.
you don't get focused on too
Yeah,
sharp details.
So I think this is a good point, because when we were trying to make the CNN, we thought the key distinction between the different artists would have been the brush strokes, which is something that requires high resolution and which you wouldn't want to blur. So the ResNet itself would have actually picked up on the frequency of different features within different eras instead of the brush strokes itself.
By removing that one class, kind of moves the goalpost. You said that you had one class that didn't have enough samples and it wasn't doing that well, so you just kind of removed it.
Right.
If you're defining your problem ahead of time and then you just change the goalpost midway, then it's not representative of how well your model actually performs on what you set out to do.
Yeah, that's a fair point.
So that's just one comment. And then for your confusion matrix, it seemed to confuse all of the one era as the other era, but not the other way around. So do you have any insights for why that was, if you go to that first confusion matrix you had?
No, we actually haven't thought of that yet. But that would
There's
be...
only 3 in the bottom left, but 21 in the top right.
No, I don't have any theory for that. I'll fill you in on that with the final report. That was something interesting to look into.
Great. Any questions, comments?